Hello community! Today we're gonna change our perspective. We're gonna look at machine learning ML accelerators, like I show you here, at ML compilers and at ML programming languages. What can they tell us about the future? And which language should we learn? Where should we run our systems? So let's start at the very beginning. Hardware. We have two ML accelerators currently. And a current generation of NVIDIA is Hopper architecture, the H100, our Tensor Core GPU that you see here on the left-hand side. And of course, Google has its own ASICs. This is the TPU version 4, where you have those famous tensor processing unit. Now, let's have a look at this in a little bit more detail when we compare it to the ML programming languages. You know PyTorch, you know TensorFlow, and you should know and love JAX. So let's have a look and start with the very first ML accelerator, our classical GPU. What happened in the current generation? What is the trend? What can we deduct from this for our work, for our clients? So at first, when you look at the technical description of H100, you see that you have a transformer engine included in the NVIDIA GPU. And you say, wait, our transformer engine, BERT transformer engine, encoder decoder stacks? Yes, exactly. Do you remember that presentation from Apple when they showed you the M2 chip, where they have a media engine for 8K and ProRes, encode, decode, a specific engine on chip? Well, you would not believe it, but NVIDIA is doing this now here on the latest H100. They have a new transformer engine. And they specify that it goes up to 9 times faster if you do AI training and multiplicative 30 times faster if you do AI inference. Of course, specified or focused on LLMs, on large language models. And these are the data if you compare it to the prior generation of A100. Now, I have not access to an H100, so I cannot validate those data. This is the data that NVIDIA provides for us. Welcome to this short interruption on the technical blog of NVIDIA, the NVIDIA Hopper architecture in depth. So if we go there and we have here a beautiful H100, yes. What I want to show you is something that quite nicely shows you where they get the additional power. Where is it? Yes, you can have a look at this in detail. But what I want to show you is this one. So here we have a look at the baseline, the A100, the old generation, if you want, from NVIDIA GPUs, and we compare it with the improvement, with the better performance of the H100. So NVIDIA tells us the improvement given H100 approximately 6 times the peak compute throughput compared to an A100. So where does it come from? And if you look at this, it tells you very clearly that the most significant contribution you get from the new Tensor cores, the 2 times faster, better, beautifuler, and the transformer engine or transformer library that you have, where you get another 2 times improvement. It is not so much the streaming multiprocessors here. This just gives you 1.2. And yeah, of course, you can increase the frequency. It gives you 1.3 times better performance. But it is interesting that the new Tensor cores, so the new matrix multiplications, the new powerhouse of linear algebra, and a specific dedicated transformer engine is really where you get this additional power. So clearly we see the cloud NVIDIA GPUs are focused here on artificial intelligence, LLMs, everything that has to do with machine learning. Interesting. Yeah, you can look at the blogs and whatsoever. No, but this is out of scope. This was it for NVIDIA technical paper on the Hopper architecture. And of course, you can combine this with NVLinks. So we have here now a NVIDIA DJX SuperPod. We have 8 times the NVIDIA H100 GPUs with a total of 640 gigabytes of GPU memory, so should be sufficient for our models, and about 7.2 terabytes per second for the bidirectional GPU to GPU bandwidth. You know, when we do all this parallelism data. And they specify, or NVIDIA specify, that this superpod features up to 9 times more performance, 2 times faster networking, and high-speed scalability. Interesting. This is the current state-of-the-art GPU architecture. Now, let's look at the specific ASICs from Google, or the Tensor Processing Unit as they call it. Now, they are ML accelerators designed by Google, and they use 3 different machine learning frameworks: TensorFlow3, PyTorch, and JAX. So all 3 ML frameworks work on a TPU. You see here a TPU board. This is copyright Google. I have no access to this board. This is just what I took from their manuals. But what you should know that each TPU chip version 4 contains 2 tensor cores. And each tensor core in itself has 4 matrix multiplication units. So this is a heavy, heavy matrix multiplication beast. And you have a vector unit and a scalar unit. And if you combine 4092 chips of those TPU chips version 4, you get a TPU pod version 4 with 4000 TPU chips. And you can see here, if you're Google, you are working in this beautiful environment. So we had a look at the hardware, the ML accelerators, our GPU and our state-of-the-art TPUs. On the other side, you know, we have our ML programming languages, PyTorch, JAX, and TensorFlow. JAX, I think, will become more dominant in the future, but let's have a closer look to this. Between hardware and software, as always, you have compiler, our machine learning compiler, that transform our programming languages into machine code that runs on the hardware. Very easy explanation. Now, this compiler more or less has an XLA compiler, a TPU runtime, and a TPU driver, in case you're looking at here this TPU board. But what is interesting is that TensorFlow, of course, being from Google, and TPU being from Google, has a native support for this. JAX, coming from Google, AutoCloud, and XLA, is XLA more or less in itself, so natively here. And of course, as I told you, you can also run now PyTorch on a TPU. Beautiful. Now, what is this XLA? XLA stands for Accelerated Linear Algebra, and it is a domain-specific compiler for linear algebra. You remember, matrix, tensors, multiplication, beautifully. That can accelerate TensorFlow models, originally coming from Google, with potentially no source code changes. Now, this is beautiful. This is exactly what you want. You have your program, and whatever comes, new version of whatever, you can use it. And if you want to know, with XLA, and this is from Google itself, if you train a BERT model, a transformer model, XLA gives you a 7 times performance boost if you activate XLA. Now, this is now my presentation, how I see the world here. Remember Keras? Keras is our high-level API of TensorFlow. Beautifully, I like Keras. Then you have TensorFlow in itself, and then you have JAX. And I put it here in this order because this is how I use it. Keras is a very high-level API. TensorFlow, here we have all our TensorFlow function and whatsoever. And JAX is really a deep dive into the programming languages, very close to the compiler functionalities. So I say JAX is pure ML for research. I mean, really currently. Although, as we will see a little bit later on, if you look at TensorFlow 3 development, JAX could move up a little bit to application. TensorFlow, clear, dominant application currently. And Keras I like because you can try out so fast in Keras some beautiful things. Now, if you want to have this XLA compiler, in Keras, with Keras model, it is easy. You say kerasmodel.compile, you have your standard Adam optimizers, and then you just add parentheses, the command JIT compile equals true. This is it. Great. Now in TensorFlow, you know the TensorFlow functionality, your functions, and you also have the JIT compile is true command. And I'll tell you a little bit about JIT and XLA in a second. And we are looking here at TensorFlow 2.10, the version 2.10, just to be on the safe side that we all talk about the same version. And then with JAX, as I told you, JAX is more or less from Google. XLA is from Google, auto-cloud. JAX is auto-cloud and XLA. So we are here really close. And you have 4 beautiful commands. You have grad, so you can take the derivative of the derivative. Beautiful. You have JIT compile, and you have vector and, of course, error parallelization, which is amazing if you do multi-GPU or multi-TPU. All this is an element of JAX, and therefore amazing. Now, very short explanation. JAX uses XLA, linear algebra, to compile and run your NumPy programs on GPUs and TPUs, also in the latest version. And the nice thing is, JAX lets you just-in-time compile, JIT, your own Python functions into an XLA optimized kernels using a one function API JIT. So you get your XLA optimized kernels and you have a very simple command line, because I'm not really in depth with compiler and I love if I just have to insert certain commands. Now, parallelization. JAX uses function transformations like pmap and vmap, but here we look at the parallelization map for single program, multiple data parallel programming. This SPMD, multiple data parallel programming of multiple accelerators, so either GPU or TPU. So this is a beautiful, beautiful functionality of JAX, and I personally have to deep dive more into JAX. This is really for ML research. If you want to go down, you want to optimize it, you want to get the best performance out of it, I think you have to program it in JAX. So this is the world. I see it here on the, let's call it Google side of the world. And you have this Keras, TensorFlow, and JAX beautifully. Now, of course, you know that there's also PyTorch. And you know that PyTorch also ran on Google's TPU. So we also achieved this in PyTorch. Maybe you have to watch out a little bit more when you have your PyTorch operation on the XLA tensors. And especially if you're running multiple XLA devices with multiprocessors, do not forget that you have to take care about your XLA core, XLA model, then your distributed parallel data loader, and your distributed XLA multiprocessing engines. And yeah, if you're familiar with this, beautiful. If you're not, think about data parallelism, model parallelism, and the pipeline parallelism. I showed you we have here now this communication from Google from September 2020, optimizing TensorFlow, XLA, and JAX for the LLM training on NVIDIA's GPU, that they want leveraging the power of XLA also for NVIDIA GPUs, a performance, flexible, and extensible ML compiler built by Google. And they have this cooperation. And as you can see here, XLA for GPU. Google delivers high performance with LLMs on NVIDIA GPUs. Interesting. Because of notable technology, XLA, which supports all leading ML frameworks. I showed you TensorFlow3, JAX, and PyTorch. And over 90% of Google machine learning compilations from research and production together, 90% happen on XLA. So XLA, you should know about this. What else does Google tell us? Deep feature sets accelerates LLM model performance, and it's solving the large model challenges seen in industry today. Yes, a feature unique to XLA is this single program multi-data parallelism, automates most of the work needed to partition models across multiple core and multiple devices, making large model training significantly more scalable and performance. Now, this is beautiful. This is the power of XLA they also want to bring to the GPU, and it is already available for you on the TPU. Collaborating with NVIDIA on several exciting features and integration that will further optimize LLMs also for GPUs. Oh, here we go. Yeah, and if you dive, this is the bfloat 16 and the 32-bit floating point and whatever. This is too much for us for this video. And they announced a recently distributed tensor or a D-tensor, so distributed tensors, heaven's sake, to enable tensor storage across devices like NVIDIA GPU while allowing programs to manipulate them seamlessly. The goal of these new distributed tensors is to make parallelizing large-scale TensorFlow models across multiple devices easy, understandable, and fast. Heaven's sake, we have to learn something new in 2023. D-tensors. We also collaborate with NVIDIA in TensorFlow leveraging, JAX for GPU. So Google also focusing on JAX for the GPU and not only for the TPU. Interesting. TensorFlow for robust production-ready models and JAX with highly optimized capabilities for cutting-edge research. Yes, it is really for researchers. We are pleased to announce the unique collaboration between NVIDIA and Google engineering team to enhance TensorFlow and JAX for large deep learning models, LLMs. Both frameworks embrace NVIDIA's A100 GPUs and the H100 GPUs. Great. So JAX also on the H100. Interesting. Nice. So you see where this goes to if you have a look. Future plans. Yes, yes, yes. Beautifully. But what else I want to show you? So the picture is clear now. You have GPU NVIDIA also wanting to have this XLA ML compiler. And of course, it is a native Google TPU TensorFlow JAX compiler that natively communicates here. Beautiful. So you see, we have kind of a industrial standardization is maybe a too strong a term, a wording, but this becomes here our ML compiler. XLA might be really the future. So therefore, if we ask ourselves, hey, which of the three languages should I focus on for specific clients? Personally, I think I have to know all three of them, but to understand Keras, so add on a high-level API. So you have to understand the approach of each programming language, what you can do in each language, and how and where you can run your models for training and inference. And I think this is the reason why I do this video here. So beautiful. Now, let's look at the future on the programming language side. Keras, there was sometimes a question mark, what's happening with Keras, and there is, now that we have TensorFlow 2.10, there is this very, very strange white elephant in the room. What will happen to TensorFlow when we switch to TensorFlow 3? What will happen with Keras? What will happen with JAX? How will it be integrated? What is the future on the side of the programming language in 2023? Now, there's an answer. We have from TensorFlow some comments about TensorFlow 3. They will provide some clearer information in the second quarter of next year, 2023. And let's have a look at their communication. Is here this communication from October 20, 2022, building the future of TensorFlow, or as I call it, TensorFlow version 3. Let's have a look at this, what they propose. The future of TensorFlow has 4 pillars. It is fast and scalable. Here we go. We have XLA compilation and we have distributed computing. As I just showed you, here we are focusing on XLA compilation, make most of model training and inference workflow faster on your GPU and your CPU, building on the XLA performance wins they achieved on TPUs. And they open it up to open source collaboration as part of the Open XLA initiative. So they want to become the de facto industry standard for ML compilers. And then they have distributed computing, they have the D-tensor, the distributed tensor, a new API for large-scale model parallelism. Remember, we were talking about data parallelism, model parallelism, pipeline parallelism, and now they are also investing in model parallelism. D-tensor unlocks the future of ultra-large model training and deployments. Yes, 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 everything will be beautiful. Now, remember I told you, what about Keras? And now if they talk about applied machine learning, they tell you they will have new tools in the ecosystem, and their particular focus on Keras computer vision and Keras natural language processing packages, which will offer modular and composable components for applied computer vision and NLP use cases, plus a large array of state-of-the-art pre-trained models for Keras. Now, this is nice. So this will mean more or less they will be integrated in TensorFlow version 3. Nice, I like this. Developer resources, beautiful, ready to deploy. C++ API, yes. Deploy JAX models. Okay, this is more or less research. We are making it easier for you to deploy models developed using JAX with TensorFlow serving. Nice, nice. Simplicity, NumPy API, okay. Easier debugging, beautiful. And here I think the most important message. The future of TensorFlow, so TensorFlow version 3, will be 100% backwards compatible. My goodness! Wow, this is finally something they learned. Great. So there will be no conversion script to run or no manual changes to apply to your code. It will be full backwards compatible from TensorFlow 2 to the next version. Heaven's sake. Okay. Timeline. Preview will be second quarter 2023 next year. And this ends our outlook on the future of the ML accelerator, of the ML compiler, what will come, and the ML programming languages, how they will evolve, what new features we will see, fast, scalable, XLA compilation, distributed computing, more and more data parallelism, model parallelism, baked into TensorFlow, with Keras as a high-level API, with JAX as a really deep dive into the programming with AutoCloud and the XLA functionalities. Hey, the future looks very interesting for us. I say thank you. I hope you enjoyed this video a little bit, and I see you in the next one.